So last time we talked about bit setting, bit clearing, masking, and all that jazz. So why would you need to do that? Why would you need to do bit manipulations? Give me a use case of where you have to do it. What?
Keep the user from flipping unnecessary switches you want to use.
So filtering out inputs that you don't use,
Right.
bits that you don't use. Anything else?
True false tests.
Cool.
Create a test in just a couple of lines.
Create a test.
True false tests.
Logical expressions.
You can create it. Just, no.
That's actually a good answer. Sorry, man.
Yeah, that's like
Logical expressions.
if
Yeah.
you were going to create a program and a user had true false, 0 is false, 1 is true, but they wanted to flip 5 and a 4 and a 7, you could just mask off all the other ones to keep from
Yes.
causing a hangout.
True. Anything else? Well, some IO devices have registers too, right? And the bits in the registers may mean different things. Next week, after this week, you guys should be able to do PLP assembly for anything, except for interrupts, which we'll talk about in 2 weeks. But you should be able to develop any algorithm not requiring interrupts after this class. There's only one more operation that we're going to talk about, and you guys are set. You can write, yes, Larry?
I've been told by several people that have taken this class before with Dr. Aiken, and they were like, oh, it wasn't too bad, but learn subroutines as quickly as possible because he doesn't teach you till the very end, and you're like, my God, why didn't we learn this earlier? We could have saved a lot of time. I don't know what
Did
any
you
of
learn
that
about
means.
subroutines?
I don't know.
We did, functions.
Okay, so that's all they're talking about is just learn functions.
Yeah.
So he waited till the end of the class to teach that. Okay.
Maybe the student misunderstood. He might taught interrupt subroutines in the end of the class. I can't imagine him teaching subroutines in the end of the class.
Okay.
So he just didn't get what interrupts were. Because interrupts, it's a bit more complex, right? Because it makes the CPU jump around. And so it's a harder concept to grasp. And that's why we usually leave it after you have good understanding of what comes before, like functions. It's closely related to functions or subroutines. It's just another layer of complexity thrown in. And there's a good reason why we have interrupts, which you will see later. So, last time we learned about masking. And we wrote a little program. Some people use zero units. So a really simple example for masking. So in this program, you just want to actually look at the 2 switches and invert it and ignore the rest. Any question?
Yeah, can you touch on the NOR thing again?
Okay.
I understand that it inverts the numbers. My question is if both of the numbers you're wanting are 1, can you step through that for one more time?
Let's do a truth table. If you have any confusion on what a logic gate does. So this is a truth table for NOR. So small. There you go. What you see here? So this is just saying these are the 2 inputs for the gate, right? And this is the output of the gate. So I had to make a correction. I think Jason Zero, you said that you can NOR a value by itself to get the inversion. You were correct. So in the YouTube video, I have annotation that says that. Somebody pointed out. So this is the truth table for a NOR. So if both inputs are 0, the result is 1. Otherwise, it will return 0. If we hold the second input to 0, then we just look at this and these and this rows, right? So if the input is 0, then the result is 1. If the input is 1, the result is 0. Effectively, you just created an inverter.
It looks like the opposite of the OR gate.
It is. Raymond being a smartass. Okay, so if you input the two inputs at the same value, right? I'll say you just hook them up to the same input, or to the two inputs. And you just look at the first and the last row. Same thing, right? If the value is 0 and you plug it into the gate, you get 1 inversion. If the value is 1 and you plug it into the gate, you get 0. We just don't have a NOT gate because we have this. Any question? All right. So now we're going to talk about shifting. Shift operations. So what a shift operation is, so if you have a binary number in a register or a value, doesn't have to be a number. What it does is shift all the bits either left to the left or to the right. Why do you think we need to do this?
Shift all bits to the left and the right?
Yes.
Multiplication.
Multiplication, arithmetic. Anything else? Can you think of anything else why we would want to shift bits left or right?
We don't have enough inputs. I just know that you can buy a physical chip called an 8-bit shift register and use that to get 16 inputs on your
Bit buffers, yeah.
Yeah.
You can do that.
Be some sort of cyclic operation?
Yeah, you can have some linear feedback register to get some values for a random number, pseudo-random. But this operation can be interpreted as logical or arithmetic, right? What's the difference between a logical and arithmetic operation? What does a arithmetic operation imply?
Multiplication or addition or subtraction?
That the value is a what? A number. A logical operation doesn't have to be. It's a bit-wise operation, right? So you just take each bit as a Boolean value. But with arithmetic operation, you take the whole value as a number. That's why in a CPU you have both operations. Sometimes you just want to deal with bits. Sometimes you are computing numbers, right? Like we discussed in the first week. Very useful and fast. So the thing with shifting operation, you can actually do some arithmetic operation by combining some shifts and add, and it'll be faster than if you would just do a division. We'll talk about this later in class, later in the semester, when you can do little bit tricks like this. Or if you can't wait, you can Google how to do fast division on a CPU. Because division is slow. It's the slowest arithmetic operation in the CPU. So first, let's look at left shift. So let's say we have this number, a binary number, and we have the decimal representation 5. So when you shift it to the left, the least significant bit that the last digit vacant, you shift in 0. Right, now you have this. So the implication is, when you do a left shift, you also, if you treat the value as a number, what did you just do? You just multiplied by 2. If you shift it again, you multiply it by 2 again. Right? So every time you shift, you multiply it by 2 to the power of how many times you shifted. Do you see that? This is for left shift, and this is really fast. We haven't discussed anything about the notion of time of program execution yet. But when we talk about clock cycles, you'll see clearly how this could help us when you do calculations. So for a left shift, it's the same mechanism for logical and arithmetic. You just shift in 0, and it'll mean the same thing. Well, it's the same mechanism, but it may mean differently. Because if you're doing logical operations, you don't care what the value represents as a number. But if you do arithmetic, you do. So in PLP CPU, you have two kinds of left shift, left logical shift, shift left logical. The first one is an immediate type, where you actually give the shift amount, well, this is R type, but you give the shift amount directly in the instruction. So for example, you have this value in register 1. And if you execute this instruction, which is take register 1, shift it left twice, and store it and write it back in register 1. After executing this instruction, this is the value you'll get. You're shifting it twice, so the digit moves left twice. So 1 becomes a 4. If you look at this from arithmetic point of view, you just multiply by 2 to the power of 2, because you shift it twice. Cool? Does it make sense? Now we also have or if you do 3, you multiply by 8, etc. Right? So the 1 just keeps shifting left on the register. When you shift it 8 times, you skip a digit. Well, 2 digits. Now it becomes 256. The CPU also has left shift variable. So instead of giving the shift amount directly in the instruction, you pull it off a register. Otherwise, it's the same operation. It's just the source of where this shift amount came from. In the SLLV instruction, you pull, for example, you pull the value from register 1, and you pull the shift amount from register 2. When you execute this instruction, it'll be the same result. Why would you, can you think of a reason why you want to do this instead of using the other instruction? Can you think of a situation where you have to pull out the shift amount from a register and not just from the program directly?
Yeah, whenever you're doing some kind of arithmetic operation somewhere else and kick that answer out to a register.
Yes.
And you want to use that as your shift.
Yes. There are situations where you don't know how many times you have to shift when you read the program. It could come from some other part of the program where it computes that.
Wouldn't a calculator be a great example of that? When you put in 2 to the upper 3 in the calculator, wouldn't that be the logical verb?
Anytime you involve user input, it's variable, right? You don't know when you read the program what the user will put in. Any question on left shifts?
So you can multiply any binary number by 64 just by shifting it over 6 positions.
6 position? Are you sure? 6 position?
2, 4, 8, 16, 32,
5, 6, yes.
64.
32.
That's pretty cool.
Yes. And it's really quick.
Yeah.
So there is a hacker's book. I think it's called A Hacker's Delight. It's filled with all these tricks on how to do some arithmetic operations just by using shifts and X. Actually pretty neat. Now let's look at right shift. So let's take the same number, and what happens when we right shift? For a logical right shift, we put 0 from the left, and you just divided the number by 2. It's an integer division. So you take the floor of the result, because the bit just drops off. This is why if you try it in C or Java, if you have an int, and you do 5 over 2, what will you get? 2. Exactly the reason why when you do integer, because you don't have the precision to actually represent decimal positions. If we have time this semester, we'll talk about how to represent decimal points, decimal numbers in this class. But you see why this happens. When you go home or in your laptop, you can fire your C compiler and do int a equals 5 and do b equals 5 over 2. You'll get a 2. And that's because on an integer, that's how you represent the numbers. If you shift it again, it becomes 1. So with right shift, logical and arithmetic right shift are different. This is unlike left shift, where it's equivalent. You just put in zeros. Logical right shift does not preserve the sign. Right? So the leftmost bit represents the sign of the number, as you saw in 2's complement. But if you put 0 in, what do you think will happen? It's logically correct, but you won't get the correct arithmetic answer. I have an example later. PLP CPU only supports logical right shift. So part of the lab this week, you have to implement an arithmetic right shift using software. So the instruction is SRL, shift right logical, same like the left shift. So the second operand, you pull in the value from the register, in this case 256, and you shift it this many times. So since this is hexadecimal, so each digit represents 4-bit, right? So when you shift it to the right by 4, you basically shift this 1 over 1 digit and it becomes 16. So you divide by 16 to the 4. Any question? Yes?
Okay, say, for example, on this one, say you shifted your value 16, say you shifted.
Right.
Or what happens? Do you just everything 0?
Yeah.
Okay.
If you shifted, let's say you have 32-bit register,
Right.
and you shifted it 32 times, you just get a 0.
Okay, so there's no underflow or anything.
No, it's a logical operation.
Okay.
Yes?
Can you go back one slide where you said at the very bottom on that?
Yes.
Only supports logical right shift?
Yes. What's the confusion?
You gave us the command for left shift. What do you mean it only supports?
You'll see in a few slides.
Alright.
Right, so the other one is variable, just like left shift earlier. So instead of using including your shift amount directly to the instruction, you can pull it out from a register. So in this case, you shifted the right 3 times. So you're dividing by how many? Is it right?
But I don't understand. But
I think it's wrong. No, it's right. It's right. Shift it to the right, so divide by 2 by 2 by 2. Right, so it's correct. It's just that you pull the shift amount from a register instead of.
oh, okay.
Because you may want to do shift operation where you don't know how many you need to shift when you write a program.
Right.
So, Jason,
Yeah.
this is it.
Okay.
The difference between logical versus arithmetic. Right? For the left shift, it's the same. There's no distinction. So when you insert zeros from right, arithmetically speaking, still correct. You multiply by 2. Logically speaking, whatever. Right? You just insert zeros, and that's all you want. You just want to shift all the bits left. But for the right shift, this is not the case for negative numbers. Because if you shift in zeros, and it's a negative number, then you'll get the wrong arithmetic answer. Right? So let's have an example. This is unsigned integer. Shift right by 1. On logical shift, you pad in zeros, you still have the same answer as arithmetic, right? Because it's a positive integer. But if you have negative number, if you use logical shift, if you treat the number as a 2's complement, is that the right answer? Depends. If it's a logical shift, it is the right answer. But if it's arithmetic, it's definitely wrong. So what do you do to rectify this? You keep the sign.
How do you copy the sign? Just load it.
That's the problem in the lab. That's the problem in your lab for tomorrow. How do you take the shift amount and actually, when you do the shift, you copy the sign bit? Okay.
Which is like, north,
No.
or.
Maybe. You could. But the problem is or with what? And how did you get it
You
okay?
can mask it. Or if you have
You'll get to play around with this tomorrow. It's a fun exercise.
Is it something to do with the size of it?
What do you mean?
Just trying to think of why that wouldn't work, like ignoring the first bit.
Oh, ignoring it? You can, but you can't just ignore it like all the time. You have to make sure that if the sign is 1, you have 1. But if you have the case like this, you do want to shift in 0. Right? So you have to preserve the sign when you write shift. That's the only difference between arithmetic and logical shift. Right
Oh,
shift.
so you gotta write something that checks the first line.
Yes, yes. Any question on right shift? If you shift it again, you just copy the sign bit again, and you will get the correct answer, arithmetically speaking. But if the logical shift, they just put in zeros. So this middle operation is what the SRL instruction does in PLP CPU. Any question? No? Sounds clear? Makes sense? Like why we have this distinction? This is not a simple concept to grasp at first, but it is pretty useful. Two's complement is just wacky, but it works really well. So applications, fast arithmetic. So with masking and shifting, you can implement some of other higher level arithmetics quickly. How would you do multiplication in a computer?
Shift and add.
Yes, that's the fastest way. Or have the hardware support that actually
You still
implements
gotta
it.
know how much to add, though. That requires another calculation.
So,
Well, I guess that would be an easier calculation. But like I said, if we're going to multiply something by 64, we know if we move it over 6 times. What if we need to multiply something by 68? Well, we can move it over 6 times. That takes care of 64
And
of
add
those.
4 of them.
But now we need to multiply it by 4 and add that to it. See,
Yes.
that's okay.
So the PLP CPU does have hardware multiply, so you don't have to do that.
But that's faster than just multiplying it straight out by 68 times.
Yeah, I'm not sure how, it depends. I think it is. It's a single cycle multiply. But division, though, is very slow. How do you do division on paper? Let's say I want to ask you 797 over 16,
Yeah,
iteratively, until you run out of digits, right?
right.
Guess how's the most naive computer does it? Exactly the same, iteratively.
Takes a remainder and then divides it.
Yes. So it has to be iterative. There are tricks where you can speed up divisions on a CPU. So if you take high-speed computer arithmetic, Dr. Stein will teach you the different ways to speed up division on a CPU. It's even the big wigs still get it wrong sometimes. Like there was a division bug in Intel 386, I think, or 486, where it was a Pentium, the first Pentium in the late 90s.
Oh, Dr. Aiken. He was on that R&D team.
The what?
Dr. Aiken was on the design team for the first Pentium.
Well, I don't think it's for that one. Like he was in the validation. So what happens, like to do division, to speed it up, they have a lookup table just to start the process. So they have a bug on the lookup table. There's a wrong entry. It's such a way that the way the bug manifests is really, really rare. So there's this professor who's doing number crunching on his spreadsheet. And he's getting wrong answers on some of the input data. Like, what the heck is going on? right? And he tried to isolate everything. It all came down to the computer. The computer has to have something wrong with it. So he reported to the Intel. Intel like, no, whatever. And then it turns out it was a bug. So they have to recall lots and lots of chips, just because who knows what other ways it could manifest, right?
They just relabeled themselves runs.
Now
That's what
with
the
broken
stuff on
division, I was like, just don't do floating division, just because you may give the wrong answer. I don't think that's how you sell CPUs. They lost a lot of money, but better than not fixing it, because people will just move to somebody else if you don't stand by your product. So yeah, division is hard. Fast arithmetic, getting the bits you want. So when you start dealing with UART device next week on the PLP CPU, you'll see on a register, each bit may mean different things, and you may want to just use a few bits and not the rest. Shifting and masking will help you. Sometimes when you sample some sensors, it has 12-bit precision. But you know that the bottom 2 bits will be just noise in your application, where you can just shift down and drop off those 2 bits before you do the calculation. So that's how you prep your values for computation. Because sometimes you don't need all those bits. For example, multiplication. When you do multiply, for example, you multiply 2 8-bit numbers together. How big is the result? How many bits? At least, at most?
8 bits.
No, more.
You took 8 bits times 1, it'd just be 8 bits.
No, at the biggest case. Like how much storage space you need to actually be able to hold all possible results.
48, something like that.
No.
16.
Think of it in terms of decimal. Let's say you have 2-digit decimal numbers. You multiply them together, right? So how many decimal digits you need to hold the result? Let's say 99 times 99. Not 2 digits. 4 digits. Same with binary. If you have 2 8-bit numbers, you multiply them together, you get 16 bits. And you may not get the whole 16 bits, right? So when you do computation, sometimes you just want to drop off precision and you just shift it or mask it. There's another kind of shift, which is a roll. I'm just putting here just for completion. So basically what a roll does, can you guess what a roll does? It shifts and what? Rolls the value over. So there are applications for it, but you can do it in software if you need to. So any question on bit clearing, setting, masking, shifting, arithmetic logical shifting?
Is this what an ALU does?
Yes, part of it. ALU does all the heavy lifting. So any logical operation, any arithmetic operation will have to go through ALU. That's it, PLP assembly. So in the lab, so there are 2 algorithms I would want you to implement. The first one is modulo. Does everyone know what modulo is? What is it?
The remainder.
Do a division and get the remainder. Why would be easier if I specify it? If the divisor is a power of 2.
Right.
You should.
Again, think of it in terms of decimal. If I modulo by powers of 10s, what's so special about the result? Let's say 79 modulo 10.
0.9, it's just easy. I don't know, it's just natural.
Natural, right?
Yeah.
So your remainder will either be 1 or 0.
No. Not with powers of 2. With 2, yes, it will be just 1 or 0.
Use the power.
Powers of 2, not 2, not just 2 to the 1. Decimal again.
You have to spoon feed it to it.
651 modulo 100. What's the result?
51.
51. See a pattern? 17 modulo 10.
7.
7. You see the pattern yet?
No, keep going.
One more time.
1,923,000 modulo 1 million.
The rest of the way to say after 1 million.
Yes! Say better. It's like, what's so special about the result? When you modulo with power of 10, Stacy, please.
You drop the first digit off.
Yes.
The answer is in the question.
Yes, you just take the digits. Same with binary, with powers of 2. When you have binary, you modulo by 4. You just take the bottom 2 bits. Yes. So you see now the pattern, like how to implement this algorithm? You'll see it more. Everyone's like, no!
Well, I understood it until you said when you take 4, because it's
Modulo 4, that's a power of 2.
it's 0, right?
Okay, 4. What's 4 in binary? 100, right?
Okay.
So if you modulo with 100, knowing with the decimal, with the pattern we saw in decimal, what would be the modulo result of it?
0, 1,
1.
You just take the bottom 2 digits of the first of the input.
B2.
Computers, man. Let me open the lab.
I feel like we're just a bunch of rubes when you ask a question and you're like, so what is it? And it's just silence.
So, for
You
example,
have to tell us.
let's say we want to do this operation, right? 32 is a power of 2. Hope so. Right? 2 to the 5th power? Yes, to the 5th. So 75 is this. 32 is this. We discussed on how to do this in decimal with powers of 10s. Same thing with binary. So if this is a power of 2, you just take the bottom 5 bits of the input value. Right? Effectively, what you're doing, you're masking off the top 3 bits and just letting the bottom 5 bits through. And if you do that, turns out you get the right answer. Magic. Right? So your algorithm will need to be able to do this. Your inputs will be these 2 values. Your, what is it called? Dividend and divisor will be the inputs. And somehow you will have to be able to do this operation and return the result on your return value register. So how to get from here to here is the crux of the problem. I don't want to spoil it. It's when you get it, it's like, yes, so smart. See, this is why sometimes I hate the answer to the back of the book. Well, not hate, but sometimes it's unfortunate because I would like you to experience that moment where you actually solve it by yourself and you got it. Hey, it was clever of me. Because once I tell you how to do it, it's gone. You will not be able to get that magic ever in your life again. I always think of it that way. That's how I give you a puzzle. Right? But you get that rush when you solve it? No, man, I'm just leaving. I don't like puzzles.
Yes, I can frame it on the wall.
Yes. So the next algorithm is you have to implement arithmetic shift, which we talked about earlier. It'll be fun lab. If you get it, we'll spend like, I think each algorithm can be written like 5, 6 instructions to give you a challenge. Like this one, if you're clever, could be 3 instructions. Haha, now everybody. 3? Yeah, 3. You can do it in 3 instructions. Not even a loop. Not enough instructions for a loop. 3 instructions. Now nobody can sleep tonight. Like, how do I do that modulo in 3 instructions? Here, I think you have to do a loop for this one. If you can do something clever and not do a loop for the second algorithm, I would like to know.
Bonus points.
Bonus points. There, you have 3,000 extra points for A. That's enough.
Bonus points.
Brownie points.
The new 9,000.
The new 9,000. So any question? Looks like we're early today. Anything on the project you want to discuss?
You want our contract, you don't want forced signature?
You want a grade? Turn into Terwell tomorrow.
Hopefully it'll be there.
So
Yeah, and what if you-
I got you for the wiki. You have access, right? But I don't have your replacement.
Not yet.
Oh, you are the
No,
replacement.
it's not yet.
So send it to me so I can add you to the wiki. If you need help on updating the wiki, just let me or Cherwa know. Cherwa is the wiki expert. Okay.
Do you think you could, like maybe post like a half dozen simple projects for us to build, to get some sort of like, start simple and a little more complex, a couple things like do this, like kind of like you do in the lab, but just more so we can practice kind of on our own.
Sure.
Not trying
I
to
have a
grade
lot of
anything,
things you
I'm
can
not trying to
write.
get any- But I'm just saying, I learned better, how to do it, like, I write code at work.
See, so give me 2 minutes. So first 4 weeks, like the idea is when I teach this class, I want to have for you to have knowledge on how to write something. After this, I would barely have any slides. I would just have PLP tool open, you can just write programs.
Awesome.
So if you have a laptop, or if you want to bring your desktop computer or whatever, so you can code along, sure. If that helps, if you have a laptop and you want to bring and code with us, it'll be, yeah. Because all the basic, we learn functions, we learn stack, we learn loop, we learn branches, that's it. You can write all kinds of algorithms. So if you have something in mind, let's say, I want to do a switch statement. All right, I'll just open the PLP tool and start coding in class. So the first 4, it sounds like we're just lecturing every week. It's like it boggles me. We barely have any homework too. And midterm is in 2 weeks. I don't know anything. But after this, it'll mostly be interactive programming in class, just to show you like how things work. Because we start talking about I/O devices. It's kind of hard to do lectures on I/O devices other than just code it, right? So don't worry. If you have a laptop, bring a laptop. Probably will help. Install PLP tool. Cool. I'll see you guys Monday.